polar coordinates are another way to plot points. We're going to look at just two-dimensional ones. Now, before I start, something to note. Let's say we have this generic point, x, y. That means the distance from here to here is x, and from here to here is y. And this is a right triangle. Oop, that's supposed to be y. And using the Pythagorean theorem, I know that if I call this r squared is equal to x squared plus y squared. Furthermore, why is this not in focus? There we go. Furthermore, if I label this angle theta, then I can see that sine of theta is equal to y over r, which means r can be written as r sine theta. Also, cosine of theta is equal to x over r, so x is r times cosine theta. So that's how the two relate to each other. So now let's talk about polar coordinates. For a polar coordinate, you're given the radius, or the distance to the point, and the angle that the ray would make with the x-axis. So, for example, let's do this. There's r, and there's my theta. So let's say I want to plot 2 pi over 3. And this, of course, is 60 degrees, as you all remember. So if I want to plot this, 60 degrees, or pi over 3, is about here. So that's the ray I'm looking at. And the distance is 2, so I mark off 2 units. That would be the point. That is pi over 3. Let's look at another one. Suppose I do 1 and 5 pi over 3. 5 pi over 3 is a little bit, it's more than 1 less than 2 pi. We're going to be in the 4th quadrant. So we're about here. So we've got 1, 2, 3, 4, 5 pi over 3. This is my angle. I need to go 1 unit out, and then I'll plot. That's the point I plot. The neat thing about polar coordinates is they're not unique in the sense that there's more than one way to describe any point. For example, let's say I want to do -2, 4 pi over 3. So I draw my axis. 4 is a little bit more than 1, so we're in the 3rd quadrant. 1, 2, 3. This is a -2, so I don't go down the axis positively. I go in the negative direction. So that's the point that I plot. These two are the same point in the xy plane. So there are infinitely many ways to describe this one point. That's what I'm saying. Now, let's go back and forth. How do we go from one to the other? Let's say I want to take the point 3 and 5 pi over 3 and convert to Cartesian coordinates. Why is this not focusing? So my x-coordinate is 3 times cosine of 5 pi over 3. So that's 3 times 5 pi over 3 is in the 4th quadrant, sorry. So cosine is positive, and cosine, the reference angle is pi over 3. So the cosine of pi over 3 is 1/2. So the x-coordinate in the Cartesian is 3/2. The y-coordinate, we get 3 times sine of 5 pi over 3. which is 3 times sine of 5 pi over 3 is the square root of 3 over 2. So the Cartesian coordinate for that point is 3 halves, negative, and negative 3 square root of 3 over 2. Okay, let's say we want to go the other direction. Go from Cartesian to polar. Look for my note on that. I had a pretty example somewhere. There it is, covered up. So let's say I want to take the point negative 3, 7, and convert to polar. Well, we know that r squared is equal to x squared plus y squared. So we have 9 plus 49. So r squared is equal to 58. And the square root of 58, we all know, is 7.61, or 62 if we round, blah, blah, blah. As for the angle, tan of theta is y over x. So my tan of theta is 7 over negative 3. If I take the theta, I'll be tan inverse of 7 over negative 3, which is 1.17 radians. So the polar coordinates for this point are 7.62, comma, that's a negative, negative 1.17 radians. So those are my polar coordinates. So now, what about graphing? We had fun with this in class the other day. I did. But instead of trying to plot points, let's get an idea of what it would be so we don't have to plot points. Suppose I give you r is equal to cosine theta. Now we know that x is equal to r cosine theta, so cosine theta is x over r. Bringing that over here, I get r is equal to x over r, so r squared is equal to x. Now, going back to our notes, we know that r squared is equal to x squared plus y squared. So looking at that, you see an x squared and y squared, they're both the same positive or negativeness, so you've got a circle here. X squared minus x, leave a space because I'm going to complete the square. Y squared equals 0. Completing the square, the coefficient here is 1. Half of 1 is 1/2. 1/2 squared is 1/4. So I add 1/4 to both sides. This becomes x minus 1/2 quantity squared plus y squared equals 1/4, which means the center of my circle is 1/2, 0, and the radius equals 1/2. If I draw that, that's 1, that's 1/2. There's my center. I've got a radius of 1/2, so I'm going to hit this point, and we're going to assume that I can draw a circle, which clearly I can't. Okay, so there's the r equals cosine theta. Similarly, like that, if we do r equals sine theta, we'll find that we have x squared y minus 1/2 squared equals 1/4. Going through the same steps. So that will be a circle that's on top. Now when I try to do this with r equals cosine of 2 theta, it's not nearly as pretty. The equation you get is nasty and you would not recognize it. So let's think about this. Let's see if I have r equals cosine of 2 theta. That means it's going to go around the circle or go around twice as fast. Now we know cosine of 0 is 1, so we're still going to start out here at 1 at the beginning. But as I run through the angles, by the time when I go from 0 to pi over 4, in my circle, when I put in the function, I will have gone from 0 to pi over 2. Now cosine goes from 1 to 0 in this range. So between 0 and pi over 4, I will go from 1 to 0. So you get something like that. As I plug in numbers between pi over 4 and pi over 2, cosine will be thinking it's going from pi over 2 to pi, which means it's going to go from 0 to -1. Okay, so what is this? If I'm going from 0 to -1, and I'm negative, so when my angles are here, I've got negative values. And I'm going to start at 0 and then make it to, when I'm at pi, I'll be at -1. That means that here, when I get to pi over 2, I'm really, wow, this is confusing. Maybe I shouldn't talk about this. I will get this. And in the next sector, I will get this. Then I will get that and that. Except it'll be much more symmetric than that. So if we've got cosine of 2 theta, remember we had if cosine of even theta, we had that many petals. Cosine of odd theta, sorry, cosine of even, we had twice as many petals. Cosine of odd theta, we had that many petals. The first petal will be centered at the x-axis if we're cosine. It's centered at the y-axis if we're sine. Let me do one more graphy thing, which is cool, I think. R equals 1 plus cosine theta. So let's think about what's going to happen here. Cosine of 0 is 1. So I'm going to start at 1 plus 1. I'm going to start at 2. Between 0 and pi, 0 and pi over 2, cosine goes from 1 down to 0. But if we're adding 1 to all this, it's going to go from 2 to 1. So by the time I get to pi over 2, I'm here. And this is really out of scale. Between pi over 2 and pi, cosine is negative, but it's always bigger than 1, less than 1 in terms of negativeness. So I'm going to have all these positive values until eventually at pi, I get a -1. So I'm here. Oops, I'm here. Cosine is an odd function, so it's going to look the same going around the other side. So you get the same thing. It looks like that. It's called a cardioid. Kind of like cardiac, like a heart, because it kind of looks like a heart. I don't think it looks like a heart. It needs to be pointy there. So we can kind of figure out what the graphs are without plotting points. If you think about the fact that you've added 1 to the radius, so your graph has gone out some, and the negative has become positive. And if we added the 1/2, that's when it did have some negative points, so that's when you had that nice little loopy in the middle. So I'm not going to ask that much of you in terms of graphing funky stuff. I will ask you about doing cosine of 2 theta or 5 theta or that sort of thing. So those are polar coordinates. I hope you enjoyed it, and I hope it was more focused than I thought it was.